Hey everybody, it's me back again. This is our last little section in the chapter. We talk about probability. So we learned how to count. Now we're going to learn how to apply it to probability. I'm going to give you just a quick overview. This is maybe a 5-minute video max. The rest we're going to do some stuff in class because, quite frankly, this textbook doesn't make this hard enough for us. So I want to define a few things here real quickly. All right, I'm going to define something called the sample space, which we'll do this, S. So S equals the sample space. The sample space is the sum total of everything that can happen in a probability event. So let's say we flip a coin. So if we flip a coin, and don't be a smart aleck, I know it's not going to land on its edge, the sample space would be heads or tails, right? Nothing to it. If I roll a die, that's die is singular for dice, die, where am I? Die, then my sample space would be 1, 2, 3, ... up to 5 and 6. That was lazy. I didn't write the 4. What a dingus. You with me? So think of it in a probability experiment. The sample space is just everything that can possibly happen. If you draw a card from a deck, the sample space would be the sum total of all of the cards. So there'd be 52 options, excluding jokers, of course. So an event, we're going to call this E. An event is simply a specific outcome. Specific outcome. So just think of it as an outcome. All right, keep it simple. So the probability of, let's say we roll a die. So an event, E could be, say, you roll an even. It could be, you could define it as rolling 6. If I roll 2 die, it could be, an event could be like rolling an 11. All right. Now, the sample space is the most important thing to define because what we need is the number or the size of the sample space. So n of S is the number of elements in a sample space. Sample space. It's really, really important. For example, let's say we roll 2 die. 2 dice, I guess, would be the right way to do this. Now, I'm gonna show you why this works out the way it is. How big is the sample space? Well, let's figure out what the sample space is first, and I'm going to do this in kind of a clever way because a lot of people don't really see this. Let's say I've got a green die and a red die, so I can roll a 1, a 2, a 3, a 4, a 5, or a 6, right? And then let's say that I have a red die, and I can do the same. I can do a 1, a 2, a 3, a 4, a 5, or a 6. So if I think about this, watch. If this combination comes up, if I do this little matrix, this would be a 1 on the green die and a 1 on the red die. Let's say that I follow this combination out here. Let's do 3 and 2. So this combination out here would be a 3, get out of there, would be a 3 on the green die and a 2 on the red die. I could write these as ordered pairs, but I'm not going to insult you. Now notice, though, that if I roll a 2 on the green die and a 3 on the red die, that is a different roll. Now, it still sums to 5, but it's a different roll because the die were different. All right? So, I could fill this entire matrix in if I wanted to, but it's relatively easy to see that the sample space, this would be the if I filled this whole thing in, this would be the sample space, and the size of the sample space, n of S, I usually do a little script thing, don't I, is equal to 36. Another way to think about this is how many outcomes are there for rolling 1 die? There are 6. How many outcomes are there for rolling a second die? There are 6. I am making 1 roll of 2 die, so they are grouped together. So the fundamental principle of counting comes into play, and it's 6 times 6, which is 36 as well. You can do that without having to go through this entire matrix. All right? So that makes sense? Now, let's talk about the probability of an event. It's so easy. And then we'll play around with this rolling die, these 2 die things, and I'll do like a card problem as well. And then we'll be done. The probability of an event, this is literally, you say this literally as probability of an event. In this case, I've named that event E. is simple. I just add up, or I count the number of ways that the event can occur, and I divide it by the total number in the sample space. Now, this is a real set theoretic way to define probability, all right? But it makes sense, right, if you think about it. Okay, so the number of ways an event can occur divided by the number in the sample space. So let's do the probability of rolling a 7 with 2 die. So this is, again, 2 dice. And what's the probability that you roll a 7? Well, all I have to do is I got to go through and I got to count the 7s. Well, do you agree that 1 6 is definitely a 7? Right? If I roll a 1 on the green and a 6 on the red, that's a 7. 6 on the green, 1 on the red, that's a 7. 5 2 and 2 5, definitely a 7. 4 3, definitely a 7. 3 4, definitely a 7. So there are 1, 2, 3, 4, 5, 6 ways to roll a 7, right? So that's the number of ways I can roll a 7 divided by the number in the sample space, which you already determined was 36. The number of ways to roll a 7 is 6 divided by 36. 6, sorry. 6 divided by 36 is 1/6. So the probability is 1/6 that given 2 die, if I roll it, then I'm going to roll a 7. That's the highest probability of all the rolls. You could actually go through and count why that is. There's a probability of 1/36 that you will roll double 1s. There's a probability of 1/36 that you will roll a 12. Now, that doesn't mean that if I roll the die 36 times that I'm guaranteed to get exactly 1/12. It means that over the course of many, 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 many rolls, on average, I will get 1 out of 36 12s. Okay? That's easy, right? Nothing to it. I hope you may or may not have seen this notation for probability before, but that doesn't matter. All right, let's talk about another